A place can be covered in ice, surrounded by ocean, and still be a desert. Antarctica is the largest desert on Earth. Meanwhile, some coastal deserts sit beside an entire ocean and may go years with almost no measurable rain. So deserts are not simply places that are hot, sandy, or far from water. They appear wherever the atmosphere repeatedly fails to deliver enough moisture. A desert is usually defined by precipitation, not temperature. A common rule of thumb is less than about 250 millimeters, or 10 inches, of rain and snow per year. That is not a perfect border. Climate scientists also look at evaporation, seasonality, soil, and how much water is available to living things. Still, the basic idea is simple. Very little water arrives, and much of what does arrive may disappear quickly. Look at a world map, and many deserts form two loose belts, one north of the equator and one south. The Sahara and Arabian deserts occupy part of the northern belt. The deserts of Australia, southern Africa, and western South America sit in the southern one. This pattern comes from the planet's large-scale air circulation. Near the equator, strong sunlight heats the surface. Warm, moist air rises, cools, and drops much of its water as heavy tropical rain. High above the ground, that air spreads north and south. By the time it sinks again around 30 degrees latitude, it has already lost a lot of moisture. Sinking air also becomes warmer as pressure increases, which lowers its relative humidity and discourages cloud formation. This loop is called a Hadley cell. On a weather app, high pressure often means a clear little sun icon. Over the subtropics, the same physics can dominate for months. Air is descending rather than rising, clouds struggle to grow, and storms are often pushed elsewhere. That sounds minor, but it matters. Repeat that pattern across thousands of years, and a dry climate can shape an entire continent. The Sahara is the clearest example, but even there the explanation is not just hot air. Its latitude places much of it under subtropical high pressure. Continental size matters too. Moisture from the Atlantic, Mediterranean, and Indian Ocean does not reach every part equally. Mountains, seasonal wind shifts, and the West African monsoon all change where rain falls. The result is a huge region with rocky plateaus, gravel plains, salt flats, dry valleys, and sand seas. The postcard dunes are only one part of it. Now put a mountain range in the path of moist air. The air is forced upward along the windward slope. As it rises, it cools, water vapor condenses, and rain or snow falls. After crossing the peaks, the air descends on the other side. It warms and dries, leaving the downwind region in a rain shadow. Drive east across California's Sierra Nevada, and the change can be abrupt. Forested slopes give way to dry basins and pale ground. The Great Basin and parts of the Mojave are dry partly because Pacific moisture is squeezed out over mountain ranges before the air reaches them. The same broad mechanism helps create dry regions behind the Andes and the Himalayas. A rain shadow can be surprisingly local. One side of a mountain may support thick vegetation, while the other side has shrubs separated by bare soil. A few dozen kilometers can make the difference. You can see it in a boring way too. Wet windshield, then dry road, then dust collecting around the edge of the car door. The Atacama Desert adds another mechanism. It lies on the western side of South America, near the sinking branch of the Hadley circulation, and the Andes block moisture arriving from the east. Along the coast, the cold Humboldt current cools the lower atmosphere. Cool air can produce fog and low clouds, but it does not easily rise into the tall storm clouds that deliver heavy rain. So a place beside the Pacific Ocean can remain extremely dry. In parts of the Atacama, fog wets a jacket or beads on a metal railing, while the ground receives almost no useful rainfall. The Namib Desert in southwestern Africa works in a similar coastal setting, influenced by cold ocean water and frequent fog. Some beetles and plants can collect moisture from that fog. It is water, just not the kind that arrives in a proper rainstorm and soaks deep into the soil. Distance from the ocean creates another kind of desert. The center of a large continent may be so far from major moisture sources that air masses lose much of their water before arriving. The Gobi is a cold desert, shaped by continental position, mountain barriers, and strong seasonal temperature changes. Winter there is not a warm sea of dunes. It can be bitterly cold, with bare rock, gravel, and frozen ground. Then there are polar deserts. Cold air can hold very little water vapor, and the interiors of Antarctica and parts of the Arctic receive very little precipitation. Snow may remain for centuries because temperatures stay low, but that does not mean much new water is falling each year. A freezer full of old ice is not the same thing as a place with frequent snowfall. This is where the usual picture of a desert starts to fall apart. Heat helps water evaporate quickly in many deserts, but heat is not required. Sand is not required either. What matters is a long-term shortage of available moisture. Some deserts are hot, some are cold. Some have dunes, and some look like a parking lot made from broken stone. Deserts can also change. Between roughly 11 and 5,000 years ago, during the African humid period, large parts of today's Sahara were much greener. Lakes, grasslands, and human communities occupied areas that are now extremely dry. Small changes in Earth's orbit altered the distribution of summer sunlight, strengthened the North African monsoon, and pushed rainfall farther north. As that orbital pattern shifted, the monsoon weakened and the region dried. That does not mean the Sahara flips from green to desert on a neat schedule like a kitchen timer. Vegetation, dust, lakes, ocean temperatures, and atmospheric circulation can reinforce or weaken the change. Scientists reconstruct the past using lake sediments, pollen, ancient shorelines, and chemical signals preserved in marine mud. The exact timing varies by location. The larger point is solid. Deserts are not permanent fixtures painted onto the planet. Rain itself can behave oddly in a desert. Dry soil may become hard or crusted, and sparse vegetation provides little protection. When a rare storm arrives, water can rush over the surface instead of soaking in. A dry channel can turn into a dangerous flash flood far from the place where rain actually fell. Then the water drains away, the surface dries, and the landscape returns to dust and stone. People can make drylands less resilient. Removing vegetation, overgrazing, poorly managed irrigation, soil erosion, and repeated cultivation can reduce the land's ability to hold water and support plants. This process is called desertification, but the word is often misunderstood. It does not simply mean that an existing desert is marching forward like a wall of sand. It means productive land in arid or semi-arid regions is being degraded by climatic variations and human activity. A field does not need to become a dune to be damaged. The soil may lose organic matter, form a crust, become salty after irrigation, or blow away during dry weather. A farmer notices weaker crops. A well has to be pumped deeper. After a heavy shower, muddy water leaves the field instead of entering the ground. Fine, but this is where it gets messy. Drought, land use, poverty, policy, and climate can all interact, so one cause rarely explains every degraded dryland. Climate change is expected to alter rainfall, evaporation, and atmospheric circulation, but the effects will not be identical everywhere. Some dry regions may become drier, while others may receive more intense rain or shift seasonally. A wetter year also does not automatically repair damaged soil. Estimates depend on the region and the model, and local land management still matters. Deserts exist because Earth moves heat and water unevenly. The equator lifts wet air. Subtropical circulation sends dry air downward. Mountains wring moisture from passing winds. Cold currents stabilize coastal air. Continental interiors sit far from oceans, and polar cold locks moisture out of the atmosphere. In many places, several of these mechanisms stack together. So the next time a desert looks empty, it is worth remembering how much had to happen to create that emptiness. Air crossed an ocean, climbed a mountain, cooled, rained, descended, and warmed. Currents moved cold water along a coast. Monsoons shifted. Ice accumulated one thin snowfall at a time. A desert is not a blank part of the world. It is a visible record of where Earth's water went instead.
Thanks for watching! If you enjoyed the video, please like, subscribe, and leave a comment below. See you in the next one!